I have with me today Professor Balasubramanian from the Civil and Environmental Engineering Department of NUS. As you know, this is part of a series of informal videos on the heroes of NUS in R&D. Bala recently received 2 awards from the Institution of Chemical Engineers Singapore, the Research Project of the Year Award in October 2015, and the Sustainable Technology Award. So I'm here to ask Bala just a few questions.
Sure.
The whole area of carbon dioxide absorption is very important, especially because Singapore is very fossil dependent, even though we have the cleanest fossil fuels. So can you tell me what innovative materials are you using to absorb the CO2?
Our research has been motivated by 3 key research questions. And the first question is, can we come up with low cost or cost effective porous carbons, especially for natural materials, and preferably from waste materials.
Or biomass.
Right. And the second question is, can we make biomass derived activated carbons better than what's commercially available in the market? And the third research question that we asked ourselves is, can we sort of regenerate and reuse repeatedly and the same porous carbon with no compromise in the integrity of the material or its performance? So then we did exploratory research to come up with answers to 3 key questions that I shared with you. So then we sort of considered using a variety of feedstocks and particularly waste materials. And then so what sort of occurred to us is, like, we are surrounded by countries where palm oil industry has been growing over the last decade or so. And in fact, we are generating about 85% of the palm oil and within this region. So we're talking about Indonesia, Malaysia, and also Thailand together. So we are producing about just roughly about 45 to 50 million tons of palm oil. But what has been documented in the literature is that the palm oil trees, about 10% is converted into oil. The 90% would simply end up in the environment as waste materials.
This is like an empty fruit bunches.
Empty fruit bunch.
Yeah.
So the empty fruit bunches are either discarded in the environment or they're openly burnt, contributing to the case problem that we seem to be experiencing year after year. In particular, this year, it lasted for about 2.5 months. So we thought that this is sort of a resource that seems to be out of place as a waste material. And so we thought we could sort of utilize this waste material and try to make porous carbon out of it.
So you have to activate it,
Exactly,
carburize it in some form.
Absolutely. So then we came up with this technology called hydrothermal carbonization, which I'm sure you're quite familiar with. So then we use this hydrothermal carbonization technology to activate carbon in situ with a chemical reagent. So the chemical reagent we add causes the porosity of the carbon, and the technology by itself would get rid of all the functional groups that are typically attached to biomass, like oxygen, hydrogen, nitrogen, and so on.
So you basically increase the absorptive capacity.
Exactly. So we do the carbonization, at the same time we create porosity, the use of a chemical reagent at a particular temperature, and in the end we come up with a highly hydrophobic material with a very high surface area. We're talking about 2,500 meters square per gram, which is far higher than what you get typically from commercial activated carbon. So on top of it, it's also hydrophobic and it has porosity, high porosity. We're talking about microporous materials, less than 2 nanometers.
Yeah, so it's actually nanoporous.
Exactly, yeah. So that's the thing about this. It also has a lot of other innovative attributes which I can share with you if you have time. And so other important attributes are, for example, this material has very high absorption capacity, which is an important factor to consider when it comes to using absorption-based technology on a large scale. In addition, it also has very fast kinetics. It's
Okay,
even
the
more
kinetics of adsorption.
Exactly.
Right.
So he has a tendency to uptake CO2 at a much faster rate compared to other materials, and is also able to retain the material and within the pores, which are typically hydrophobic, and more importantly, it has a very high selectivity over here. So we are talking about interference from nitrogen,
Right.
which is dominating in terms of concentration as compared to carbon dioxide.
Yeah, and especially in Singapore, where you actually have a very clean feedstock, the percentage CO2 in the stacks are much lower than in, let's say, coal plants or oil-fired plants.
Absolutely.
Yeah.
So then we can demonstrate that the material we have prepared has a very high selectivity and it has a large preference towards carbon dioxide. On top of that, the material also has chemical resistance toward acidic gases and alkaline gases. And so then we are able to regenerate the material over here, and the reason why we are able to regenerate it with minimal energy consumption is because it has a low heat of absorption.
Okay.
And so the CO2 absorption is an exothermic reaction, as we all know. So it releases some heat. The heat released is enormous. It's going to reduce the rate of absorption of carbon dioxide.
Right.
It becomes counterproductive. So in this case, the heat of absorption happens to be the lowest compared to other competing absorbent materials that are commercially available. So given that, although it's a exothermic reaction, we have low amount of heat being released, being absorbed by the material, and therefore the kinetics is still very good.
We had mentioned regeneration, but because this is very, you have a vast amount of these materials.
Yeah.
And the CO2 has been now really sequestered or absorbed in there.
Yes.
When you regenerate it,
Yes.
Tell me what would you then do with the CO2 that's being released? That's one question.
Right.
The other one is if you don't regenerate it, can this material itself have other values?
Yeah.
Turn it into a component of asphalt or brakes or something. Yeah, just these two questions, because that will then give the audience, okay, what are the practical applications of it?
Well, thank you for asking these important questions, Michael. And we did ponder over these questions while doing research. And the good thing is that this material can be regenerated with a minimal energy penalty. So that's an additional attractive feature of the material we can prepare.
And it's just through heating, really?
Yeah, exactly.
Okay.
And then we are able to selectively remove carbon dioxide. The next question is like, what do we do with the carbon dioxide?
Yeah. Exactly.
Well, the conventional wisdom is to store it. We don't want to go with that option.
Yeah.
So instead, we have been asking ourselves, can we utilize carbon
Yeah.
as a material for industrial production of chemicals, fuels, and so on? So we are talking about utilization. Okay. At the same time, we also have the option in terms of storing hydrogen and other gases in the same material as well over here. We are talking about CCUS, rather than CCU or CCS.
Yeah.
So carbon capture, utilization, and storage. So depending on where the material is used, where this application is sought, and the kind of environment that we live in, we can go for the two options. In places where we think we need to have some chemicals because of lack of natural resources, then we can produce chemicals indigenously after we capture carbon dioxide. So we are talking about artificial photosynthesis. And so this is the kind of direction we are going currently.
Like gas to liquids kind of stuff.
Exactly.
As you well know, last year we ran the largest conference on carbon dioxide
Yes.
utilization in the US. But for your thesis or your research, it's
Yes.
mainly on the capture of it. You did not really study now the utilization of it, although you know the different pathways.
Yeah. So the conference you mentioned certainly was a very good conference. In fact, we participated in the conference, we made contributions. And following carbon capture, which is is happening satisfactorily, and now we are focusing our attention more towards utilization of carbon dioxide. And then, so we could make a number of chemicals, but then it's not so easy in practice because it's also going to consume energy.
Exactly, or hydrogen, and then we have done the analysis where even just for Singapore, if you take it and do formic acid, it will swamp the world supply of formic acid.
Absolutely. We are also able to make graphene
Okay.
out of this biomass. And then what we are planning to do and what is currently happening in terms of research is to try to observe the sunlight and then trigger chemical reactions.
Yeah.
And by capturing CO2 and returning onto the surface and then turning it into other chemicals.
But you may need
Which are
some catalysts
industrial
on that. You have to.
Yeah, exactly. As you rightly pointed out, we are using some catalyst over here.
Okay.
So that's the kind of application we are focusing on at this point.
So now we are looking at the
Yes.
visualization or the transformation using photocatalytic system.
Correct. And then there are a number of possible reactions that could occur. But certainly we got to find out whether they're thermodynamically feasible.
Right.
And then it will add a value in terms of the value capture that we're talking about, Singapore's context. So although we have identified a number of potential reactions that could occur through photochemical transformation of carbon dioxide, we are trying to sort of trim the list
Yeah.
and come up with selected chemicals that we think will add a value to the market in Singapore's context. At the same time, we don't have to use a number of unit operations in order to make the chemical following the capture of CO2. So that's the kind of
Try to do it in situ or something.
in situ.
You've heard Bala telling us about the capture sequence and all of that. Now I want him to summarize by saying what are the three criterion which he then satisfies with this area of research, and then we can wrap it up.
Yeah, so basically the technology that we have developed for the conversion of waste materials, in particular EFP biomass to porous carbon, is very simple in nature, is very versatile, is scalable, and more importantly, is not dependent on the kind of feedstock we use for carbonization. And so when we develop the technology and then use it for potential applications, we are guided by three important criteria. The criteria here, as Michael pointed out before, we are talking about energy criteria, environmental criteria, and more importantly, economic criteria. So we want to add a value in terms of manufacturing or growth of national economy or green economy, so to say. So this is where we want to make contributions to the kind of technology we get developed, which is basically converting waste to biomass like EFP, empty food bunch biomass, into value-added products, including activated carbons.
Yeah. So there you have it. Thank you very much,
Thank you so
Bala,
much.
and you can see why he is an award winner, or 2 award winners. Thank you.
Thank you so much. I want to thank you guys for the support.